Okay, BYP working on the A4 assembly in the Hewlett-Packard 8660. In the previous few videos, I've been setting up the eventuality of having a double expletive deleted situation of big capacitor cans that can't be moved because they're in amongst sensitive RF circuits. So far, I haven't run into anything extremely sensitive until now. There's the A4 assembly. If you see the coil with the spread out turns, that's a 100 megahertz oscillator, fairly high frequency. The spread turns that aren't symmetrical are where that has been bent for tuning. That bottom turn right there is bent down. Down here, another one of those on a bit of a form. Down here, U1, see the metal heat sink? See the ceramic cap and the gold-plated leads? Look out. Very special integrated circuit. That's a 100 megahertz amplifier. And U1, a divide by 5 circuit, and that heat sink is at minus 10 volts. That's a supply for that IC. I've never seen one like that. The gotcha here is up here. 500 megahertz output, A4J9, coming from Q6, L9, C note 3. Let's go find Q6. Well, right there's Q6. Do you see an inductor with a tap? I don't. Do you see an inductor with a tap there? Oh yeah, right there. The tap is where the wire is soldered on. Right there below the transistor cam with the green dot, and to the right of the 103M101 blue capacitor. That's a transformer with a tap. There's no transformer or coil there. Did they forget to put it in? No, they didn't, because C note 3 on L9 takes us down to L3. L8 and L9 are part of the printed circuit board. A 10-yard penalty for calling it a printed circuit board, because it isn't, but that's what everybody calls it. But part of the board. And, race fans, you're looking at L9. Right there, CQ6, the collector terminal at the bottom, right there above that round capacitor with a screwdriver slot above the legend Q6. That trace coming down is the inductor. And it branches over to the right to that wire going to that coaxial jack 500 megahertz out. That's the tap. And down here, look what happens. That coil at 500 megahertz runs directly under that 22 microfarad capacitor can. And that can is separated by a dielectric, a plastic, and it sneaks back under there. It's real hard to see. It goes under and turns, and you can just see a piece of the trace between the greenish inductor on the left and a 22 UF capacitor on the right. Between them is that trace going up to the top lead of that inductor, and the inductor goes to the minus 10 volt supply. So that capacitor is there. And you'd never suspect in a schematic that there was coupling between that capacitor and way over here, L9. So for circuit analysis, I drew in the coupling between the C4 capacitor body, which goes to the minus 10 volt supply, and the top of that inductor. And the top of that inductor is also through dividers at the minus 10 volt source. So the top of that coil is closer to the minus 10 volt supply maybe than ground. But that minus 10 volts through 3830 ohms through 8250 ohms is at some negative potential, apparently. That's sure what it looks like because I don't see it going into any voltage source over here. But there's coupling from the top of L9 to that capacitor body to the minus 10 volt supply over there. So this is what I've been practicing for, and I've never done this before, this detailed replacement of leaving the old bodies in. And on some of them, I cut the capacitor body and just pulled it away because that's a lower frequency circuit there. But here I've cut the capacitor lead on the top. I bent the lead to the board away and left that capacitor exactly where it was. So hopefully it doesn't change the coupling in there. When doing this kind of thing, you got to be real careful with these schematics. These schematics are not made by the engineers that design this stuff. They're made by drafters and technical writers and all that. And C12 is incorrectly drawn on a schematic. It's on a minus 10 volt source, and if you look at the schematic symbol, it shows the positive capacitor lead at a negative voltage. That's wrong. So I drew in the correct symbol, marked the correct plus, marked it C20. Oops. Correct my mistake, marked it C12, T for tantalum. But following the schematic would result in someone putting the capacitor in backwards, and the tantalum is quite likely to explode because they're solid and they're dipped in epoxy. And incidentally, that's old notation for capacitors. The curved plate is minus, the straight plate is plus. In the old days, variables used to be designated by that, the curved plate with the arrow on it. Then that changed to just two parallel plates with a line through, with an arrow through. But notice somebody went to some trouble to submarine that gray cable under that board, and there's nothing down there on that corner of the board. And note that shielded cable, but the shield is folded back and insulated on both ends. So it would not be good to ground that cable. I don't know exactly why they did it, and I'm not going to change it either, because it's like that for a reason. But this is typical for how I've been replacing these capacitors. Form loops on the ends around the original leads, crimp them down, solder them, and then come back later and cut the capacitor can, because if the can's cut out first, the wire remaining on the board is so flimsy you can't crimp a new capacitor to it. So then you got to chase it around with a soldering iron and try to get the solder to tack down and harden before the capacitor moves. So leaving the capacitor body in and soldering first greatly reduces the chance of bad solder joints. And there's a heart-stopping O expletive. Down below the Q5 legend, see the dipped red silver mica come down and go to the right to that dark component with the black and red band. See the solder blob on that trace below? There was contamination in the solder joints on top and bottom of that little, I think that's a resistor. But when it was heated, especially down below, you can see that the flux has exploded outwards. And that happened on the top lead. When it was heated, that exploded and blew solder out on that trace. And it is a hair's breadth away from shorting. So these are the kind of things that we got to inspect for, and why we got to have clean parts going into the assembly process, because just that can blow solder balls across the board a considerable distance and cause shorts. And if you look just to the left of that yellow tantalum that's out of focus, see the solder balls underneath on that trace? I got to get in there and take that stuff out. So these are the kind of mistakes we got to look for. There have been enough mistakes in this unit. I'm surprised it worked, but it did. So KBYP did.